Alright, welcome back. So I'm going to continue applying for this job here. The job is an AGI engineer working for aigo.ai. Be working pretty much side by side with Peter Voss, who's a very interesting character. Claims to be one of the first people to use the term AGI. Interested in some interesting things. Has a personal site up here, so ethics and lots of writings. Very prolific writing. So interesting person would be very interesting to work for. So it's a kind of a unconventional job application. Basically, you just need to send an email, but the email needs to demonstrate that you've read some things that they. So if we go down to careers, we can see they have a posting. So and we can see what that posting asks for. So it's reviewing the articles in white paper, and it's unclear which white paper. There are three white papers up, but I'm gonna try to read all three, and emailing questions, and then an explanation of why you'd be a great fit. So kind of an untraditional job application. Normally you um, don't apply that way. But let's continue. So the next so I'm currently reading one of the white papers. This is the longest one that I'm reading, so hopefully I should be able to get this in. I confirmed that I can that'd be fine to have this submitted by Friday. So that's my goal. Hopefully that will be possible. A lot of this paper, it's 38 pages, but multiple of those pages are just citations. So yeah, so the references start on page 28. So it looks like 10 full pages are just citations, which is great. Which I don't need to do for the purposes of applying for this post. Although it would be a good thing to do afterwards to prepare for the actual job, to review some of those references. But so that means I'm making pretty good time. It's Tuesday, so assuming I use this time well here, I've got an hour and I can pause it and do Pomodoro stuff. This should okay. I should make a dent in it, and yeah, be all good for Friday. So the study in citation 97 introduces a post-training adjustment method to mitigate CF. CF stands for catastrophic forgetting. It's a problem in large language in outputs of large language models. They catastrophically forget parts of the input. So if you give them a list and you say, I want you to remember these 5 names. Now it doesn't work with just 5. It's if you feed it a lot of information, it's more likely to happen. But you say Bill, William, Sarah, Jennifer, and Tiffany. It is likely that it will forget the middle name, Sarah. It'll likely completely forget that. So it'll just throughout the rest of its replies catastrophically forget a critical piece of information. That's a main problem with AI right now. So the study in citation 97 introduces a post-training adjustment method to mitigate catastrophic forgetting and improve continual learning. That's the other problem in AI right now. In order for it to be an AGI, it needs to be able to learn in real time and continually improve upon its learning. In MLLM, so that's a multimodal large language model. The model tailor retains the pre-trained parameters and replaces fewer fine-tuned parameters up to 10%. Building on the tailor metaphor that selects patches for a garment, it identifies and adjusts a minimal parameter set as a sparse mask, or the model patch, from the fine-tuned model. It extracts the patch by inspecting parameter and loss changes to identify a critical subset of fine-tuned parameters essential for learning a target task. Moreover, it decorates the patch by compensating weights with an inverse Hessian matrix to enhance the performance on both current and previous tasks. So Hessian matrix is new to me. This is honestly a bit of a long shot, I feel like, but it's an unconventional job, right? It's not your typical job. He's kind of looking for prior AI experience is not required. So I might be the perfect candidate for this job. I'm gonna get this job application in and see where it goes from there. And I'll include a link to this playlist. So I just gotta be careful not to get intimidated, because I'm sure I'll learn as I go. I want a job like that where I learn a lot of new things. Okay, so this is all new to me. Hessian matrix. Yeah, I want a job where, especially, I'm learning new, like, fundamental, like, mathematical knowledge that a job where I can, like, study math would be pretty awesome. There's not a lot of jobs like that out there, in my opinion. Alright, so moreover, it decorates the patch, and I'm not sure what a patch is, or the model patch. Just a minimal parameter set as a sparse mask, so that's what a model patch is. So it's just the minimal parameter set as a sparse mask by compensating weights with an inverse Hessian matrix to enhance the performance on both current and previous tasks. The method is evaluated using instruct blip and LLAVA dash 1.5 MMLMs for VQA and image captioning tasks, and available benchmark datasets. And this might be a typo here. This might might be MLLMs. We'll get a jargon table for this from the AI, and we'll see if that's the case. The results show improved continual learning while preserving inherent pre-trained capabilities compared to traditional fine-tuning, and adaptability in multitask scenarios. However, the effectiveness of extracted and decorated patches remains to be verified in more complex and open domains. So let's get a jargon table for this whole paragraph. It's just filled with jargon. So create a jargon table. Create a jargon table for the following paragraph. Alright, and let's see what it just does with that. We've got pro mode here, O1 pro mode for $200 a month, so hopefully it will do a good job on it. Alright, and while that's working, we can read the next one, so we'll probably have to make another jargon table after that. Alright, so contrastive learning, COL, learns meaningful representations from large-scale unlabeled data by maximizing the agreement of the positive pairs formed by the original instance and its corresponding augmented instance, while minimizing the agreement with the negative pairs formed by other instances. Contrastive learning can also use supervised learning by adding label information based on category discrimination. Some image classification tasks include prototypes, which force the embedding of instances closer to their corresponding prototypes in the embedding space, while moving them away from other prototypes. Con- Contrastive language vision pre-training, CLIP, represents a VLM pre-trained on large image text datasets. The model contains one image and one text encoder. COL, contrastive learning, is conducted during pre-training, where a correctly paired image and text is a positive pair. In contrast, incorrectly paired image and text belonging to distinct image text pairs are a negative pair. The prediction is formed by finding the closest text embedding given the image. CLIP is known for its ability to perform zero-shot image classification, which can easily classify images based on natural language descriptions without specific training in those categories. The study from Citation 101 introduced zero-shot continual learning, ZSCL, to address the catastrophic forgetting in continual learning with the VLM through feature distillation and parameters ensemble. So VLM, we get from the jargon table, which might be ready. Let me check it. It looks like VLM didn't make it into the jargon table. Okay, so we'll read this and then make another one. So distilling the initial model features on a reference dataset significantly enhances its performance. Parameter ensemble among different training stages effectively mitigates the forgetting issue. The study also processed a multi-domain task incremental learning (MTIL) benchmark to evaluate learning tasks from different domains, surpassing state-of-the-art methods. However, a limitation is that an excessive high-quality reference dataset is needed. Sometimes the pre-training dataset must be filtered out of errors or existing information updated. Conducting these tasks on a given dataset is difficult. The details are available here. Alright, so I've been adding a star to these. Kind of clutters up my stars, but to have all of this starred, it, I think makes sense. So let's get a jargon table for this. Okay, so I'm saying good. Now create another jargon table for this text. Alright, and let's look through the jargon table. So yep, CF catastrophic forgetting, a phenomenon where a machine learning model retrains sequentially on multiple tasks, forgets previously learned tasks as it learns new ones. Continual learning, a method of training models to learn new tasks over time without forgiving previous learned information. Okay. What's the one model tailor is a metaphorical concept used in the study similar to tailor adjusting a garment. The model tailor identifies minimal sets of parameters, a model patch to adjust or replace, thereby improving the model's performance on a new task without losing old capabilities. Alright. So did this let me do this. So we're gonna highlight this, and then oops, I thought there was a way I could highlight it and oh, I guess I thought there was a way you could highlight it and Huh. I guess that doesn't exist anymore for this. Uh, okay. Well, let's just copy it. And we'll say yes or no. Do you think MMLM is a typo in the following text? I am notorious for being able to see typos where no one else can, and I think I found one in their white paper. So that'd be a question for them. Why can't you hire an editor to find your typos? All right, but let's see the jargon table. There was one term that, uh, oh yeah, VLM is a vision language model. So a machine learning model that processes both visual, image, and textual language inputs, learning a shared representation for both modalities. Okay. All right, and then we have a MMLM typo check. Yeah, so it does appear to be a yep, exactly. This acronym was introduced, but isn't defined separately and does not correspond to a well-known distinct term. So, and it's only one letter permutation away. So it's likely a typographical error. Ha! Yeah. So I'm really good at I'm exceptionally good at finding typos, and I found one there. All right, so language guidance for prompt-based continual learning (LGCL) introduce a introduces a pool of learnable prompts to store task information. The prompts instruct a pre-trained image encoder in solving tasks, allowing the model to learn without storing large amounts of data or increasing the number of learnable parameters. Prompt-based continual learning methods leverage pre-trained vision encoders and learn prompts that guide the model in solving new tasks based on stored knowledge without extra storage or additional parameters. The rationale is that the model can describe the task's label space with the shared language space despite task distribution variations between tasks. Mapping to this space can mitigate CF, leading to performance improvement. The study from Citation 24 introduces task and class level language guidance. Task level guidance encodes the language feature matching to the classes represented with the prompt keys in the pool. Relevant prompts are selected from the pool based on the keys to guide a pre-trained model. Class level guidance encodes the language feature matching the ground truth class from the pre-trained model output. The levels are evaluated using BERT, Roberta, and CLIP pre-trained textual encoder models. Although the approach mitigates CF without including additional trainable parameters, prompting does not teach the model in a traditional sense since its underlying weights are unchanged. Sequential fine-tuning, SCQ, described in Citation 102, examined fine-tuning PLMs to learn a sequence of 15 downstream tasks of four types, including text and intent classification, named entity recognition, and relation extraction. For encoder backbones, the study used BERT versions with 109 and 335 million parameters. Decoder backbones used GPT-2, 124 and 774 million parameters, and GPT Neo X, 19 million to 1.21 billion parameters. The study revealed that the inherent anti-forgetting ability of PLMs comes from the pre-training stage, and that classifiers learned in SEQ cause forgetting. Specifically, the relative position changes between the class embeddings in classifiers and the features extracted by the PLMs led to decreased performance on old tasks even when PLMs do not forget. Besides, the experiments focused on IL classification on tasks, so that's IL's incremental learning. Let's get a jargon table for this one because it's getting a little bit out of control for this one as well. So, build a jargon table for the following text. Alright, so class incremental learning, CLL, is employed by vision language models, VLM, to learn general representations from textual information without forgetting previously learned tasks. Projection fusion proof approach alleviates CF in VLM. The model appends linear task-specific information by mapping the projected features. Learning new tasks extends new projections while freezing old ones. The projections indicate proof learns new classes while retaining the old ones with state-of-the-art classification performance. Nevertheless, learning new tasks enlarges the model size and requires more training exemplars, increasing memory and computation requirements. Alright, let's see what the jargon table looks like. So, I think it was PET. I forgot what that means. Oh, PLMs. Yeah, pre-trained language models. So, large language models that are trained on massive amounts of unlabeled text data before being fine-tuned for specific downstream tasks. So, examples include BERT and GPT variants. Yeah, I forgot about that. And then PLMs, so the inherent capability, so PLMs, pre-trained models, language models, have an inherent capability to retain previously learned knowledge from their initial pre-training, reducing the degree of catastrophic forgetting when fine-tuned. What is most susceptible to catastrophic forgetting? Alright, well, anyway, moving on. So the study in citation 105 includes a cold clip, a method for open domain CL, continual learning, so ODCL, in vision language models that enables them to learn from a sequence of tasks with non-overlapping classes without forgetting previously learned knowledge. ColdClip uses a class vocabulary and a prompt-based approach to learn task-specific patterns and refine class embeddings, while mitigating forgetting through replay-free cross-domain vocabulary learning. It simultaneously learns task prompts and class embeddings in Clip's text and image encoders. The model outperformed state-of-the-art methods concerning classification accuracy and forgetting on 11 datasets for open domain CL in both CIL and task incremental learning TIL scenarios. However, real-world ODCL can use very different datasets representing incoming tasks, which may exhibit significant domain gaps and large variations in class correlations and data distributions. The study in citation 106 investigated the acquisition of recommendation capabilities through LLMs in context learning. In particular, the interaction data, collaborative information, is utilized in the instruction of tuning of pre-trained LLMs to improve performance in warm and cold recommendation scenarios. The scenarios subscribe sufficient or limited or no historical interaction data between users and items, respectively. The resulting LLM encodes collaborative information in an external model, mapping it to the input token embeddings. Collaborative embeddings formed in this way improve recommendations without modifying the LLM itself. The researchers fine tuned the Vicuna 7 billion parameters model using the movie recommendation dataset Movie Lens with 1 million interactions and the Amazon book dataset with around 4 million interactions. However, the results confirm the necessity of incorporating high quality collaborative information and suggest that the improved performance in both scenarios primarily comes from this information and not from adjustable fine tuning instructions. An approach to ingrain learning in real time capabilities is an integration of LLMs with knowledge graphs, KGs. Neurosymbolic computing combines neural networks, NNs, pattern recognition capabilities with KGs, knowledge graphs, reasoning capabilities by either compressing knowledge structures into vectorized representations suitable for NNs or linking neural patterns with a symbolic knowledge by extracting pertinent pattern information. Currently, the LLM-KG integration is mainly implemented in learning pipelines with separate LLM and KG components, losing some of the original schematics in the produced representations in both techniques. Alright, so, okay. Alright, anyways, moving on. So, Dynamind is a continual learning pipeline that combines pre-trained LLMs, GPT-4, Llama, and Falcon models, VDs, which serve as memory, and symbolic planners, coordinator, searcher, browser, responder, and discriminator. Essentially, the memory and symbolic planners are used to populate and verify prompt templates so that LLMs are guided to extract new information without tuning their parameters. In other words, it conducts prompting without updating model weights. The framework and experiment details are available here. So I'll star that. Okay. So next section. Let's see how long I've been reading here. So it's been about a half an hour. So I might want to take a quick break. Let's see if there's a logical stopping point. Not really. Yeah, there really isn't one. So I need to get to page 27 to be complete. Alright, so incremental prompt learning employs pre trained LLMs to help robotic systems learn new tasks. In particular, the content of the current scene, what the what the robot perceives, is used to construct prompts as LLM inputs, ChatGPT in this case. The responses are fed into the robot's memory to generate interaction examples containing prompts and responses based on which the robot learns new actions. The robot learns from the interaction with an LLM. This approach does not improve the capabilities of the LLM itself and is susceptible to hallucinations requiring human supervision in generating interaction examples. Similarly, uh, League Plus Plus uses LLMs to facilitate deep reinforcement learning (DRL) and task and motion planning (TAMP) for continuous learning of new skills in robotic devices. With League Plus Plus, an LLM accepts task decomposition and operators involved in generating skill plans for TAMP, which is task and motion planning. Another LLM then generates skill rewards for RL skill learning, which a formal planner further verifies. This process enables online autonomous learning for long horizon tasks. Although the framework demonstrates superior performance compared to baselines in 4 simulated task domains, it doesn't enhance CL in the LLMs employed. Decision making workflows for autonomous vehicles use standard and chain of thought prompting of LLMs in highway scenarios to generate driving plans and influence driving behaviors through verbal commands. Although workflows are improved and verified in a simulated environment, they do not enhance LLM's capabilities. Auto GPT plus P utilizes LLM with formal planners for affordance-based Task planning. In particular, the study represents an affordance-based scene representation combining object detection and automatic object affordance mapping (OAM) using ChatGPT. The OAM associates object classes with the set of affordances assigned to the instances of those classes. The scene objects are then represented as a set of object affordance pair (OAP). The study employs different prompting techniques for querying ChatGPT for OAMs, which are then used to generate plans and explore and suggest alternatives in case of missing objects needed to achieve a task goal specified by the user in NL. The proposed planning architecture was evaluated by simulating 150 scenarios with different tasks of humanoid robots, such as picking and replacing, handover, pouring, chopping, heating, wiping, and sorting. However, given the probabilistic representation of the OAPs, which are object affordance pairs, obtained from LLM outputs, generated plans need external verification for improved accuracy in real world deployment, which is interesting. Oh, okay. This one kind of screams to be hided out as well. So I guess it's like because all you're doing is like what is the highest. So and an OAP, let's unpack that. So an OP is an object affordance pair. Uh, let's ask the the LLM to write this out in plainer English. All right. Hopefully it does a good job with that. 'Cause that one it feels like it screams out to me to be highlighted, but I don't exactly understand why. All right, so continual optimal policy regularization (COPR) is a method that aligns LLMs with human preferences in a CL setting. Reinforcement learning from human feedback-based techniques often require retraining when encountering new queries or feedback, as human preferences vary across domains or tasks. The method computes the distribution of optimal policy bypassing the partition function and then regularizes the policy based on optimal distribution to mitigate catastrophic forgetting and improve preference learning. Besides, it can learn from unenabled data by maintaining a scoring module similar to the reward model, making it flexible for continual learning without human feedback. Although the method outperforms existing continual learning methods in the task and domain CL settings, it still needs RL, HF reward, and policy models to start from, which may reflect the preferences of a particular user group and induce a bias when optimizing the current policy. Alright, so let's see this. Oh, it's still going, so let's get the details piecing together. How LLM outputs with their probabilistic representation need external validation for real world accuracy. This involves confirming the feasibility of planned actions with the object. Yeah, that makes sense. Okay. Alright, so the study in citation 117 proposes a post-training, a post-pre-training method for LLMs that expands transformer blocks. It starts with an LLM pre-trained on a massive unlabeled corpus. Then it deploys backbone expansion and fine-tunes the expanded blocks using only a new corpus while freezing the blocks inherited from the base model. This way it aims to improve the model's knowledge without CF. The model after post pre-training can be used for instruction tuning. The method was demonstrated using coding and mathematics training data, resulting in Llama Pro 8.3b obtained from Llama 2-7b as the base model. Llama Pro and its instruction following pre-tuned version, Llama Pro Instruct, have outperformed existing Llama-based open models for general tasks, programming, and mathematics. This result, however, is based on an increase in model size and evaluation in specific applications, coding and mathematics. Therefore, the effectiveness of the block expansion method in more complex and open-ended domains is yet to be verified. Alright, so here's a logical pause point, so let's get down there to there. Processing long input sequences during inference is challenging for LLMs as they perform poorly on outputs whose lengths are larger than those in training sequences. Self-extend is a method that aims to handle long contexts without fine-tuning. It extends the LLM's context window by structuring the attention component into a group and a neighbor attention. The group attention manages long-distance token relationships by tracking the dependencies among distant tokens. The neighbor or standard attention tracks dependencies among adjacent or approximate tokens based on a specified range. The attention matrices are merged and the softmax operation is applied. This way, the method connects the distant positions at inference time to positions seen during training so that LLM can handle longer texts without additional fine-tuning. Extensive evaluations with Llama-2 and its successors, Phi-2, Mistral, and Sonar, on short context tasks, synthetic and real-world long context tasks, and language modeling tasks have consistently demonstrated the effectiveness of self-extend. However, this extension in context window length comes at the cost of increased computation as it requires calculating extra attention across all query key pairs. The results are available here. Alright, so I started that. Let me go ahead and take a bit of a longer break now, because this is kind of a logical stopping point. This is going to discuss the model and experiment data here. So it's kind of a logical place to take a break. I'm at the 40-minute mark. So Yeah, okay, cool. I like this. I like this. So, because large language models only provide uncertain or best guess information about how objects can be used, the action plans they create may not always be accurate. To make sure these plans actually work when put into practice, it's necessary to check them against real world evidence or some external verification process rather than relying on the model's output alone. So there could be a factor it's not considering, or something. So give me an example of give me an example of a plan that fails when put into practice. I'm just curious about that because like that's like robots can't general very well. So like maybe like it's like I'll ask you about that. All right, so I'll read to the next one now. This is it's not that much. Oh, you know what? Let's get to 2.2 before taking a break. All right, so rehearsal based methods use past training data, which may be unavailable or non existent at inference time. Self synthesized rehearsal (SSR) utilizes the LLM to produce synthetic rehearsal data. It fine tunes the base LLM to create synthetic examples through I-CL with few shot examples. The examples are collected from the previous data or created manually. Next, it employs the latest LLM to refine outputs using the synthetic instances. Finally, it selects diverse high quality synthetic instances augmented with currently available data for future rehearsals. SSR employs Lambda 2 7B. Uh, not Lambda, Llama. Yeah, and then Llama 2 7B chat. And Alpaca 7B. Wait, Alpaca's a kind of llama, right? Oh, no, it's different from a llama. It's quite a bit different from a llama. Oh, now the llama won't even. Oh, okay. Okay, it still does pop up as an animal. So, is it not a alpaca? What's the difference between? I guess they look quite a bit different. Alpaca has more fur. They're domesticated. The llamas are. Oh, both of them are. I'm confused. Oh, alpaca are llamas. Or a particular kind of alpaca is a llama. Oh, and llama is spelled. Wait. Oh, okay. Oh. Okay, so they're visibly shorter and they have more wool. Llamas are taller and are very athletic, but they don't have very good wool to harvest. All right, well that's a major difference. I didn't know that alpacas and llamas were so different. All right, in Alpaca 7B, LLMs using uh, LoRa, which I forget stands for. It stands for low something something. and supernatural instructions, super NI, a comprehensive instruction using benchmark dataset. Oh, a comprehensive instruction tuning benchmark dataset. The results indicate that SSR is more data efficient and receives superior or comparable state of the art performance. Moreover, it preserves LLM's pre trained generalization capabilities. However, synthetic instances may contain unreliable content from biases in data and may not always show the best generalization ability on unseen tasks. Without user generated training data, some approaches train LLMs from synthetic data. The study from citation 49 proposes an interactive inference that allows users to prompt the GPT-4 LLM by providing specific instructions where the model responses are cleaned and used for instruction tuning the base model. The system, named Online Training Using External Interactions, supports 3 prompt types as input data augmentation techniques: textual instructions, aka instruction guided learning; textual instructions with offline sources, aka document driven learning; and textual instructions with online sources, aka web search enabled learning. The instructions generate corresponding training data, which are further filtered for quality control, toxic or biased responses, and used to train the base model. The system was compared with the online parameter invariant method prompting and the offline parameter variant method training all parameters. The former uses Llama 2 7B chat as the base model to produce answers from few shot prompts. The latter method trains the model with external annotated training data and then uses the same prompts for the test set as in the former. Although the system has reduced training costs regarding the data amount compared to the offline method, it still underperforms in accuracy, which remains similar when increasing the number of training examples. The Scalable Language Model, SLM, adapts the base LLM to new tasks from distinct domains while keeping its performance on the older tasks. SLM integrates the task distribution within the vector space retrieval into the knowledge model for knowledge expansion and management. The dynamic task related knowledge retrieval DTKR component identifies the most relevant knowledge for each input instance, assuming each task has a distinct data distribution in the vector space. It preserves relevant knowledge by compiling weight increments through low rank adaptation to decrease computation. And I think that's what LORA is, low rank adaptation. Yeah. The joint adaptive reparameterization, JARI, then uses these weight increments to obtain adaptive reparameterization of the pre-trained model, aligning it with the downstream tasks based on their distribution. The SLM is efficient and stable on existing benchmarks, achieving state-of-the-art performance on different base models, including BERT, T5, and Llama 2. However, the method introduces a separate retrieval component, increasing memory and computational costs. The model and experiment data are available here, so I will start it. Okay, so imagine a robot's been given a series of instructions generated by a language model about how to pick up a glass of water from a table and bring it to a person. The plan might look like this. Move forward until you are next to the table, reach out and pick up the glass of the water, turn around and move towards the person, offer the glass of water to that person. When the robot tries in the real world, step 1 might work fine and moves close to the table, but at step 2, the plan doesn't account for the exact size or shape of the glass, or the fact that the table is slightly higher than expected. As a result, the person's hand might miss the glass or knock it over instead of picking it up. Because the language model didn't know the precise dimensions of the table or glass and didn't instruct the robot to adjust its grip or position, the plan ends up failing in practice. Okay, so you can imagine a lot of these sorts of examples. Like, imagine that they didn't know which person to hand it to, and there's multiple people, and it hands it to the wrong person. Imagine that it doesn't know which glass to pick up, and there's one glass half full of water, one glass with no water at all, and it picks up the nearest glass, and that glass doesn't have any water. So how does it know that the glass actually has water in it? So like you can imagine so you could easily imagine how important it is to do real world practical testing rather than just doing everything theoretical, because in the end you can't account for every single possible situation out there. You just have to observe and add things in hindsight. Alright, so the study from citation 131 combined learning rate rewarm, learning rate redecay, and replay techniques to compare the performance with full data retraining. The study trained the GPT Neo X decoder-only model and compared the performance by measuring final loss and LLM evaluation benchmarks. The results show that LLMs can be successfully adapted by combining the above elements. The performance matches the retraining baseline with a compute fraction. In particular, rewarming and redecaying the LR from a large to a small value in pre-training improves adaptation to new tasks. The study also suggests 5% replay as a default value and using more replay with significant distribution shifts. While the experiments updated the model on 2 subsequent tasks, the approach's efficacy in settings involving larger distribution shifts, model and dataset scales, infinite LR schedules, growing models, and tokenizer adaptation for handling larger changes in data distribution remains to be verified. So that brings me to section 2.2, which is meta learning. That's a really good place to cut it and do another video. I'm getting very much closer to my goal. I think having this application in by the end of Friday is going to be possible. So that being said, thanks for watching this part, which is part 3, and stay tuned for part 4.